SwayamPrabha. Digital India. Educated India.
Okay, welcome. This is the second lecture for the course Element of Solar Energy, and in the last lecture what we have seen, we have introduced you to the course, what is the basic motivation, okay, and then we have talked about the electromagnetic radiation, the basics of it, and then the structure of sun, okay. So, these are the major things we covered, and we also talked about the solar radiation spectrum. Okay. Now, this lecture what we are going to cover are the following. Okay. So, first we have looked at sun, so we will need to look at earth now, okay, and then the sun earth relationship, which actually only part of it we will see in this lecture, and it will continue for few lectures from now onwards, okay. And then we will talk about solar constant, what do we mean by that, and we will also talk about the extraterrestrial radiation, okay, and how it varies, and we will revisit the solar radiation spectrum with the new information that we learn in this class. And we will also, if possible, if we can cover, we can also go to the sun earth relationship, revolution and other things. Okay. So, let us start. So, the first thing is we first need to know about earth, because we live on it, we do not see how big or small it is, but we know about it, okay. So, again we can approximate it as a sphere, just like the sun, okay, and its diameter is approximately these many kilometers. So, about 13,000 kilometers, okay. And again reminding you about building up this intuition of how big the sun is compared to earth, it is 110 times in diameter, okay. Now, if we talk about earth, so it rotates around its axis approximately 24 hours, that is what our day length is, right. So, again that is approximate, and it revolves around the sun approximately 365.25 days. Okay. So, this 1/4 day that we are left with in counting every year, what we adjust is in the leap year, right. We add one extra day to adjust this 1/4 day. Okay. So, this is about Earth, and the interesting part of Earth is that the orbit of revolution is not circular, but elliptic. Okay. And that makes the things much more interesting than the circular one. So, Sun lies on one of the foci of the ellipse. Okay. And we know, and we will again see how it gives rise to many interesting stuff. So, this eccentricity of this of the Earth's orbit is such that the distance between the Sun and the Earth it varies by 1.7%. Okay. So, the distance between the Sun and the Earth is not fixed, it varies by a small amount, but that gives rise to again the variation in solar radiation that is reached from the Sun to the Earth. Okay. So, when we have a variation, what we do? We need to find the mean. Okay. So, because whenever we have a change, a variation, if we do not have the mean, then it is difficult to enumerate that variation. So, the mean is, or the mean Sun Earth distance and it is also called one astronomical unit. Okay. So, that is how we measure a very long distance in cosmology. Another the most commonly used one is the light year, but here this one astronomical unit we often measure often use in terms of these smaller distances like Sun, Earth, Sun, Moon, Earth, Moon, and all these things. Okay. So, that distance is actually 1.495 into 10 to the power 11 meter. Okay. That is the Sun Earth distance mean. Now, if we draw the Sun and Earth, then let us say this is the big sphere which is the Sun, and the small sphere which is Earth. So, this is Sun and this is Earth. Okay. Now, if we have an observer on Earth, okay, what will it see? It will see a sphere in the sky, right. The Sun will be a big sphere in the sky, and what is the value? What is the value of this diameter? The sun diameter is about 1.39 into 10 to the power 9 meter, okay, and earth dia is this many kilometers. Okay. So, and the distance between these two centers, that is the mean sun earth distance, that is 1.495 into 10 to the power 11 meter, okay, and that distance varies, variation is plus minus 1.7%. Okay. Now, I was talking about an observer on the earth. So, let us say O. What will it see? It will see a sphere in the sky, that what you all see, and the solid angle that sphere will subtend would be 32 minute. This is a very important number that will come again and again in the course. This 32 minute angle it will subtend the sphere sun. Okay. Now, what we need to know is the I mean, we are continuing with this sun earth relationship, and all the radiation emanating from the sun, only a mole fraction is reaching the earth, right, that you can understand, because you have a you have the sun here and all the radiation that are going around. Only if this is your earth and this 32 minute, that is the solid angle it is making, that sun, okay, and the among everything what is coming. So, whatever is coming towards earth, only a small fraction of this whole radiation sphere that it is making, only a small fraction is actually getting intercepted by the earth. Okay. So, this is very important. Now, next we will define the solar constant. What is the solar constant? It is the radiation intensity of solar radiation outside, this is very important, okay, outside the Earth's atmosphere, okay, because atmosphere changes lot of things in the radiation. So, what we are trying to fix now is beyond the atmosphere. When there is no atmosphere, what is the radiation intensity there, and it also depends on the sun earth distance. So, to fix it, what we do, that at the mean sun earth distance, this is also very important. okay, and that is called solar constant. So, what we can see that if this is our earth and we have a layer of atmosphere on top of this. Okay. So, when solar radiation is coming, what we are measuring here is that we are placing a plane just outside the atmosphere and measuring the intensity on top of this plane. Okay. So, and again when the sun and earth is at the mean distance. Okay. Now, there are lot of different methods. So, methods for measuring this solar constant. It got evolved with time. Okay. And it varies, the value varied from to 1395 watt per meter square. Okay. So, during the last century there are a lot of effort went into this measuring this solar constant, which is important quantity, and what is the value currently accepted. So, value is 1367 watt per meter square. Okay. So, that is the solar constant. So, we are first defining few things so that we can use them later. Okay. Now, we will talk about this extraterrestrial radiation. Okay. What do you mean by terrestrial? Terrestrial means related to earth, means related to earth. So, basically in this case whatever is reaching the surface of the earth, that is what we call terrestrial radiation. Reaching the surface of the earth we call terrestrial radiation. Okay. And what is remaining outside? So, this extra terrestrial, in this case it means outside the atmosphere. As I said that atmosphere alters the solar radiation significantly, and that is why it is important that we know what is coming at the boundary of the atmosphere, and that is called extraterrestrial radiation. Okay. And we designate it with ION. So, I stands for, I mean why the name came, it talks about the intensity, that is why I, and this O is the outside atmosphere. Okay. So, this particular O is designated there, and this N stands for normal. That means the measurement is done on a plane kept normal to the incoming radiation. Clear? So, we will talk about these different designations of intensities later as well. So, this is the first time we are introducing it. So, ION stands for the extraterrestrial radiation which is normal to the plane, I mean on the plane which is normal to the radiation itself. Now, of course, we have seen that ISC is the solar constant which is the intensity at mean distance outside the atmosphere, and that has to be related to this ION, right. So, this is the actual radiation normal to the direction of radiation, okay, at the edge of the edge of the atmosphere. Okay. So, these has to be, they have to be related, right. What is that relation? Again, lot of effort went into that, and ultimately what relation we got is the following. So, let me first write, then I will explain. Okay. So, this is the relationship we get for the ION which is called the extraterrestrial radiation, and ISC which is the solar constant. Okay. So, you can see that this particular, so this is the variability part, right, and it is a function of n, right. So, what is this n? N is the number of day starting from January 1. Okay. So, for February 10 you will have n equal to 31 plus 10, that means 41. Okay. So, for 365 days in a year you can find a particular value of n, and that n goes in this expression which will determine what would be the extraterrestrial radiation intensity on that particular day. And here you remember that we do not bring the complication that are coming for the leap year and other things. Okay. So, we assume that we have 365 days only, and the amount of error that you incur by not considering the details of leap year is so minute that you do not care about it. Okay. So, for engineering accuracy you do not need to consider leap year, you just consider it to be a normal year with 365 days. Okay. So, that is the relationship that we get for the extraterrestrial radiation and the solar constant. Now, if you plot this particular relation, how will it look? Again I should emphasize that this is not to the scale, this is just for illustration. Okay. So, here let us plot month. Okay. So, like January, February and so on till December. Okay. And on the other axis we plot extraterrestrial radiation, basically ION, and the unit will be watt per meter square. Okay. Now, if you look at, and these will be these are the values, let us say it varies between 1300 to 1400. Okay. So, the values will be like this. Okay. So, here you notice that at the mean sun earth distance you will have some value which is about this 1367 watt per meter square, and that is the value we called ISC or solar constant. Okay. And interesting thing that you note here is that, so if this is January, if this is January and this is December, and they have to be periodic, right. So, for the next year also it will start from here and these two points should match. Okay. This point and this point should match. Now, and here you notice that this January, December, these are winter times, right. At winter times we have the highest intensity that is available. Okay. So, this I should note here that at winter we obtain highest ION. Isn't this counterintuitive? What do you think? We expect that at winter the amount of radiation, solar radiation that are coming will be less than the summer, right. That is our normal intuition goes by. But these are measured data. So, this particular plot is showing that at summer ION is the lowest. So, this is counterintuitive, right. But think in more general term, like when we have winter. So, in northern hemisphere we have winter, at the same time in the southern hemisphere it is summer, right. So, summer in southern hemisphere. So, what we can see, and this is only outside the atmosphere, okay. And you have to, ION means what? You have to keep the measuring plane perpendicular to the direction of radiation, and it is outside the atmosphere. So, all the atmospheric change and as well as the angle of incidence are neglected in this ION measurement, right. So, that is why we are getting something which is counterintuitive, and in the winter we are getting the maximum extraterrestrial radiation, and in the summer we are getting the lowest. Okay. So, this point is an interesting point, and again I should suggest that you should pause the video for now and then you think of it, okay, and get this internalized, because intuitions only when let me give you an example of intuition. Like if you tell a child to hold a glass, if a glass is made of steel or it is made of paper, okay, we adults what we do, for the steel glass we hold it more strongly, and for the paper glass we hold it much soft, in a much softer way. Okay. That way what we do, we ensure that the paper glass does not crumble. Okay. Now, when we actually hold the glass, we do not think of it like purposefully, right. It comes automatically for an adult, but for a child it does not come automatically. So, a child holds the glass with the same force, and you often see that the glass crumbles if it is a paper glass. Okay, so, that way we build up intuition, we practice and all, and then it get internalized, then we do not have to separately think of it. Okay, here also you take a pause and think of this solar radiation, and you get it in your intuition that in the winter, or rather northern hemisphere winter, we are getting the maximum intensity possible outside the atmosphere, okay, because the distance between sun earth is maximum at that point. Okay. Even if it is counterintuitive, you get it internalized, so that you can make sense of it. Okay. Now, we promise that we will revisit the solar spectrum. Okay. Because we want to emphasize that whatever solar spectrum we have talked about in the last class, that is only for this ION or ISC, all these extraterrestrial values. Okay. Not what we receive on the surface of the earth. Okay. So, that is why we come back to it, and we how the atmosphere changes it we will talk about later, but what we want to make point here is that whenever we talk about the spectrum, this is the wavelength in micrometer. Wavelength is usually designated with lambda, and this is the, you can say, this is the spectral irradiance, okay, in watt per meter square micrometer. Okay. So, we have gotten something like this. Okay. Now, what we want to emphasize here, that the area under the curve is what? So, this area under the curve is ISC, or if you plot it for ION, you will get ION. So, the intensity, and this will be clear from the units as well. So, what is the unit of this particular spectral irradiance? It is the watt per meter square micrometer. Okay. And for ISC, the unit is watt per meter square, right. So, you can see that only when the micrometer is multiplied with this spectral irradiance unit, then only you will get watt per meter square. Okay. So, that is the point I want to mention here. This ISC or ION, that is the area under the curve, not the particular value. Okay. Now, another way to represent this is the spectral variation is by this quantity which we called f naught lambda. Okay. What is f naught lambda? It is the fraction of the solar constant associated with wavelength shorter than lambda, Okay. So, it is basically you are trying to find, okay, again if we have this particular form of the spectral irradiance, and then let us say we want to know f lambda at this particular lambda. Okay. So, what is that? So, this is the area under the curve which is shorter than the wavelength lambda. Okay. And what is ISC? ISC is the whole area under the curve. Okay. So, basically we can write f O lambda, O I am coming next. So, let us talk about this first. So, what we get? It is area under two areas. So, here on the numerator you have this particular area, and on the denominator we have this particular area. Okay. I think this is clear. Now, let me come to the O part, which is you already guessed, I guess, that this O stands for outside atmosphere, right, just like ION, this ION, O stand for outside atmosphere, or it is called extraterrestrial, right. Here also it means extraterrestrial, and lambda is for this particular lambda. Okay. So, now if we want to specify this spectral irradiance of ISC, because too many variables we cannot handle. So, that is why we have taken the solar constant only, which is outside atmosphere, okay, and we will now see what is the spectral variation for the same. So, the same thing we can, instead of graph, what we can write? We can write the numbers which is lambda for a particular wavelength. So, basically this I we cannot use multiple times. So, what we can do, this I spectral, let us say S and lambda, this is basically the spectral irradiance, and here we can write the FO lambda. Okay. So, basically if you take few values, you can list lot of these values, but let us take few of them. So, if we take lambda to be 0.25 micrometer, then this IS lambda, that will be 13.8, and this will be 0.002. So, basically if we draw this figure again, so what it means is that at 0.25 micrometer, this height would be 13.8 watt per meter square micrometer, okay, and this particular area, sorry, here this particular area, okay, will be 0.2%. So, this will be 0.002, that means 0.2% of the whole area under the curve. Whole area under the curve is nothing but ISC. Okay. So, that is how we designate the solar spectrum, and let us look at few other values, maybe at 0.5 micrometer we have the intensity 19.18 and 1918.3, and the FO lambda would be 0.216. Okay. Similarly, just like this figure, you can find out what it means. Okay. Another one value let us take at 0.8 micrometer, we have 1133.3 and this is 561. So, you can see that by 0.8 micrometer we have covered more than 50% of the total energy that is coming in, okay, total ISC. Okay. So, that is how we often measure the spectral irradiance outside the atmosphere. Okay. Now, what we can talk next? Now, what happens when solar radiation travels through the atmosphere? This particular thing we will talk about later. Okay. But there are a lot more interesting things that happen in the extraterrestrial radiation only. So, what variations happen for the extraterrestrial radiation? That is what we are going to see now. Okay. So, now we need to invoke the revolution of Earth. Okay. And the change in season. Then only we will be able to understand how this variation happens, what are the major factors, as well as it will help you develop your intuition. Okay. So, let us say that we have sun here at the center and we have an orbit. Okay. So, it is elliptical, somewhat I could make it elliptic, okay. And Earth is moving around the sun on this elliptical orbital. Okay. So, this elliptical orbit. Okay. Now, one interesting thing happens because the Earth is not revolving around the sun with its axis normal to the orbit plane, okay, or orbital plane. Okay. So, if we call this is the axis of the Earth, Okay. It is not perpendicular to the plane of the orbit. Okay. And that is the most interesting feature of the revolution of earth around the sun, and that is what makes the seasons possible on earth. Okay. So, that makes the seasons possible on earth. Okay. So, before we go into that detail, let us say that we have 4 seminally important positions of the earth on this orbit. Okay. So, everywhere the rotational axis is the north south axis. Let me just write north in every case, and in one case we have written south as well. Okay. Now, if we look at this seminal position, can you guess what? Let us say this is the position 1, this is position 2, position 3 and position 4. Okay. And this is sun. Okay. Now, this position 1, what position, I mean what would be the corresponding date, can you guess? This would be the summer in northern hemisphere, right. And because the north pole or the northern hemisphere is tilting towards the sun. So, north hemisphere is tilting towards the sun, that you can see, and this is because the orbital is the axis of the rotation is not perpendicular to the orbital plane. Okay. And the exactly opposite position, which is position 3, that will be the winter in north hemisphere, right. Because for position 3 you can see that the northern hemisphere is tilting away from the sun. So, northern hemisphere is tilting away from the sun. Okay. And what we can say that at the same position it will be, for position 3 we have summer in northern hemisphere, sorry winter in northern hemisphere and summer in southern hemisphere, right. Here we have summer in northern hemisphere and winter in southern hemisphere, right. And for position 2 and 4 we see that neither north nor south is tilted towards the sun. Okay. So, these positions we can see neither north or south is tilted towards sun. So, what we can expect? it will be neither summer nor winter, and these are called equinoxes. So, both position 2 and 4 are called equinox position, okay, because nox stands for the night, and when the day and night are equal in length, that is what we call equinox. Okay. And these extreme positions, this is called summer solstice, and this one called winter solstice. And here we have this bias, we all name it in terms of northern hemisphere. Summer solstice means summer in northern hemisphere, okay, that condition we are talking about. And for winter solstice, again winter in northern hemisphere. So, those who are watching this video from southern hemisphere, you have to reverse the intuition completely for the whole course, because that is how the nomenclature goes. Okay. Now, if we look at this earth revolution around the sun, what we understand is that there will be two extreme positions which are called solstices. And what would be the summer solstice? The date will be 21st of June, okay, that will be the longest day for the northern hemisphere and the shortest day for the southern hemisphere. Okay. And the other direction for the winter solstice, we will have 21st December, when we have the shortest day in northern hemisphere and longest day in the southern hemisphere. And for the equinoxes, again the position 2 is called the autumnal equinox, autumnal equinox, okay, and the date is 21st September. Okay. And the other equinox that we have, that we call spring equinox, which is 21st March. Again these equinoxes are named with respect to the northern hemisphere. Okay. So, fine. So, we have come to the end of this class, where we have looked at the extraterrestrial radiation, how it varies and what is solar constant, and we also looked back at the solar spectrum in the extraterrestrial radiation, and we have started the sun earth relationship in terms of the revolution around the sun and how it varies the season and what are the different nomenclature for the solstices and equinoxes. So, in the next class we will start from here and we will define the tropics, what it means, and we will take up from there. And thank you very much for your attention.